All right, let's talk about nuclear power, but probably not the kind you're thinking of. I'm talking about something that promises to be safer, cleaner, and a whole lot more abundant than anything we use today. Yep, we're diving into thorium.
So, could this be the thing? The key that finally unlocks a new era for nuclear energy? You know, one that actually solves the nagging problems that have held it back for decades? Well, let's dig in and find out.
Okay, so before we can really get why thorium is such a potential game changer, we got to talk about the status quo. We have to understand the challenges we're dealing with when it comes to the nuclear power we use right now, which is pretty much all based on uranium.
So what is the problem with our current nuclear setup? Well, it comes with some serious baggage, right? First up, the waste. We're talking about stuff that stays dangerously radioactive for over 10,000 years. Then there's the proliferation risk, the fear that the materials could be used for weapons. And the reactors themselves, they run under insane pressure, which is a huge safety issue. Oh, and on top of all that, the uranium fuel is pretty rare, and its supply is controlled by just a few countries. Okay, so with all those problems on the table, it's time to introduce our protagonist, thorium. This element, it's like it has a completely different playbook for nuclear power. A playbook that could, maybe, solve every single one of the problems we just laid out. So what exactly is this stuff?
Well, thorium is just a naturally occurring radioactive element. Simple as that. And yeah, it really was named after Thor, the Norse god of thunder, way back in 1828. Kind of fitting, don't you think, for something with this much raw potential?
Okay, this next part is maybe the most important thing to get. Thorium is fertile, not fissile, like the uranium we use in most reactors. What does that mean? Well, it means it can't start a nuclear chain reaction all by itself. It needs a kickstart. The analogy here is perfect. Think of fissile uranium as kindling. It catches fire super easily. Thorium, on the other hand, is like a big, dense log. You need some of that kindling to get it going, but man, once it's burning, it burns for a long, long time.
And this is where things get really interesting. Let's talk about availability. There's 3 to 4 times more thorium in the Earth's crust than uranium. This isn't some super rare exotic element we have to hunt for. It's everywhere, it's abundant, and it's all over the planet. I mean, that alone could totally change the whole geopolitical game of nuclear energy.
Right, so this is where thorium's unique properties start to look like, well, a set of superpowers, because it directly takes on the two biggest fears people have about nuclear power: safety and waste.
Let's hit the waste problem head on. Remember that 10,000-year headache we talked about with uranium? Yeah, forget that. Thorium waste is a whole different ballgame. We're talking about needing safe storage for maybe 300 to 500 years. Now, don't get me wrong, that's still a long time, but it's not 10,000 years. It brings the problem from a geological timescale down to a historical one. It's something we can actually wrap our heads around and manage. And to put an even finer point on it, a thorium fuel cycle creates 83% less of that really nasty, long-lived stuff, the transuranics, like plutonium. So it's not just that it makes less waste overall, it makes way less of the absolute worst kind of waste. That's a huge deal. I mean, just let that sink in for a second. 300 years versus 10,000 plus. That's not just a small improvement. It's a fundamental shift in how we could responsibly manage this kind of energy.
And the safety argument? It's just as powerful. A lot of thorium reactor designs are what we call inherently safe. That means safety is built into the physics, not just bolted on. They use passive systems, like this freeze plug idea. If the power goes out, it just melts, and gravity drains the fuel into a safe holding tank. No buttons, no computers. Plus, they operate at normal atmospheric pressure, so you can just get rid of that risk of a massive steam explosion. They are, for all intents and purposes, walk-away safe.
And this right here shows that core safety principle perfectly. It's all about something called a negative temperature coefficient. Now that sounds complicated, but it's really just a fancy way of saying that physics itself is the fail-safe. If the reactor starts to get too hot, the reaction naturally, automatically slows down. No human has to do anything. The car analogy is perfect. It's like a car that just automatically takes its foot off the gas if the engine starts to overheat. The safety is literally built into the laws of nature.
Okay, but what about the big one? Nuclear weapons. Well, it turns out thorium has a built-in anti-theft device. The reaction creates this nasty little isotope called uranium-232, and this stuff gives off intense gamma radiation that's super hard to shield. Basically, this contamination makes the fuel so dangerous and difficult to handle that trying to make a weapon out of it would be, well, a terrible, probably fatal idea. It's just not practical.
So, what about the money? How does this all stack up financially? Well, this chart gives us a pretty good idea.
Look, building the first-of-its-kind thorium reactor is not going to be cheap. But look at the long term. With fuel that's way more abundant and waste storage costs that are a fraction of what they are now, over the lifetime of the plant, thorium could end up being the clear economic winner.
Okay, I know what you're thinking. If this stuff is so amazing, safer, cleaner, more abundant, why isn't every power plant a thorium plant? And you're right to ask. It's the big question, isn't it? The answer surprisingly has less to do with science and a whole lot more to do with history.
So picture this. It's the 1940s, the dawn of the nuclear age. Scientists are at a fork in the road. They knew about thorium, but they chose uranium for one very specific reason. It can make plutonium for bombs. The Cold War kicked in, and that pretty much sealed the deal. Even though a thorium reactor was successfully tested in the 60s, the world's focus was locked on uranium for the arms race. So thorium didn't get abandoned because it didn't work. It got sidelined because of military politics. It's only now, in our search for clean energy, that we're seeing this global comeback for thorium research.
But let's be real, it's not like we can just flip a switch. There are some serious hurdles to clear. For starters, we need to invent new materials, new alloys that can handle the incredibly corrosive, high-temperature liquid salts in some of these designs. Then you've got the rule books. Our regulations are all written for old-school reactors. They need a total rewrite. And remember, we still need that kindling to get the reaction started. Putting all that together, it's going to take a massive investment in research and development to make it happen.
So with those challenges in mind, let's look to the horizon. How are scientists and engineers actually tackling these problems? And what does the future for thorium really look like?
And that future is already taking shape in designs just like these. We're talking about really advanced ideas, like molten salt reactors, where the nuclear fuel is literally dissolved in a hot liquid salt, and next-generation heavy water reactors. These are the top contenders, the technologies that could finally unlock thorium's massive potential for the whole world.
And look, this isn't just some drawing on a whiteboard. It is happening right now. There's basically a global race to crack this. India has made thorium a central part of its entire long-term energy plan. China is pouring money into it, and they're super close to finishing a test reactor. Meanwhile, in the US and Europe, you've got this cool mix of startups and government labs all pushing the technology forward. The race is definitely on. So that brings us right back to where we started. Is thorium really the key to our clean energy future? Or is it still just an ambitious dream? I mean, the vision is incredible, right? Safer, cleaner, truly sustainable nuclear power. The road from the lab to lighting up our cities is still steep and full of challenges. But as we've seen, the race to get there is well underway. The question is, will we make it?